All right, let's look at the sensor first. The humanoid robots use pressure sensors at the bottom of the feet to balance the robot. Not all of them, but most of them does that. So there are so many different types of pressure sensors, but this is probably the most popular one. It's called strain gauge. I actually bought some of them. I was trying to mount them to the low cells. You'll see what are the low cells pretty soon. But these are just the 2-terminal devices. The reason I'm interested in this type of sensor is because in phase 2 of the horseshoe project, we are supposed to embed these pressure sensors to the shoes. And hopefully we can detect injuries of the feet of the horses. But we never got into phase 2. The investor just ran out of funding. It's been 2 years anyway. But I think we should explore it instead of just going through the concepts. I have the calculations. So every time I teach this class, we just go through the slides that show the calculation, but never get into the application. And you know, if I do the same thing here this semester, it's gonna be 85 minutes just myself talking, and it's been boring. I think since I have never taught a boring class. if I figure out it's people are getting bored, I will stop and do something else. I just couldn't teach to someone with a poker face and getting bored and getting sleepy there. It doesn't make sense, right? Since I was a student in these classes, pretty much all the classes when I was in college, I just sleep. I'm not interested at all. So today's lecture will be short, and I won't have a lecture on Thursday. I'll give you guys the time to finish this project. Not really difficult, just one single project. You just need to get the data read into the serial monitor. And do you need to display that? No, you don't have to. So because the horseshoe project, remember the sensors embedded into the shoes, and it's sent out to the data center. Remember the accelerometer, so you have a wireless communication. So the first also take baby steps. The first step is to sense the data from, not this one. I will give you the low cells. I'll show you why. I mean, you can see every slot has 2 sensors, but this one only has 1 because I just damaged it. I'm going to show you why you shouldn't play with these sensors. You should play with the low cells. And the pressure sensor embedded into the shoe, and you should get the data through wireless communication. So the second task is to send it out. You don't need the SD card this time. Just send it out to another one, and the other one receive the data and display to the serial monitor. So this is a very reasonable 1-week task, I think. I'll show you some pictures pretty soon, but these are resistors. It's just a wire, winded wire being printed on the plastic film. It's a resistor, it's a metal wire, and have 2 terminals. Whenever you bend it, just don't bend it too much. That's how I damaged the first one. If you bend it slightly, if it's being deformed slightly, it's going to change the resistance of the 2 terminals. And that's how you can sense the pressure. Okay. And do you know what's the most common application, the everyday thing you have seen, probably in your house, which has this type of sensor in there? No. The remote is just a push button. Yeah. Not this one. The bathroom scale. And I removed the cover of my bathroom scale and was looking at the low cells. All these things are made in China, right? So, and all the low cells are made in China, probably from the same company. Anyway, and I was looking at the low cells, exactly the same low cell I'm gonna have for you guys. Same thing, and even for the sensors, the ADCs, same company, same chip. Yeah, but we are not making a bathroom scale. It's gonna be the same library we're going to use, the same sensor, but just 1, not 4, because the ones you have in the bathroom has 4 in there. So one quick quiz question: If you bend this sensor, are you going to have a huge resistance change or tiny resistance change in your mind? Tiny. It's very small. And the reason I damaged it, I was trying to see a big difference. I bent it, there's no change on the multimeter. 0.01 ohms change. I was like, what? Probably not working properly. Let's bend it more. Then I broke it. Yeah. So you cannot directly use these ones just as a pressure sensor. The resistance change is too small, so you have to put them in a kind of circuit structure. I'm going to show you the calculation pretty soon. It's called Wheatstone bridge. Have to put it into the bridge in order to sense very minor changes of the resistance. Okay, now let's look at the calculation right now. And also, why you need a low cell? Because you need these plastic films to be mounted to a rigid structure. Otherwise, it's going to be damaged really quickly. So see what are the low cells pretty soon. But let's go through the calculation really quick, and we will head into the lab, and I'll give you the parts so you can start working on it. The first one is called the quarter bridge. So all the bridges are called Wheatstone bridge. I think that's the last name of the one invented this circuit. Oh, DGE. The first one is a quarter bridge. Just put one string gauge into the bridge. Here's a voltage, it's called excitation voltage. It's just a voltage input. And here's R. That's a string gauge, so it's going to have a delta R here whenever you deform it, give a pressure to it. And here's V1, here's V2, okay? And that's a delta V to be sensed by what? How do you sense the delta V? What's the sensor for voltage? It's kind of very odd. No, it's a very odd question, but what's the sensor to sense voltage? Come on, guys. ADCs. All the sensors senses analog signal from the environment and convert into voltage, right? So what senses voltage? ADCs. So this delta V will be shorted to where? Amplifier first, okay, and then ADCs, because it's too small. So what is delta V over here? How do we calculate delta V? So delta V equals V2 minus V1. What is V2? It's a voltage divider, right? Voltage divider here. So V2 equals VEX, that's excitation voltage, times the ratio here, which is R plus delta R, over R plus delta R. That's V2, right? Minus V1. V1 is just 1/2 of the excitation voltage with the voltage divider. Two resistors are equal. And this becomes Vx R plus delta R. And this becomes 2R plus delta R minus Vex over 2. And combine them together, you're getting Vex. Is that 2 times 2R plus delta R? And got 2 here, 2R plus 2 delta R minus 2R plus delta R. And this equals Vx 4R plus 4 delta R. No, 2 delta R. On the top, this is cancelled, and this becomes 3 delta R. No, 1 delta r, right? This minus delta r is 1 delta r. And what's next? Compared to 4r, this one is tiny. So this is very close to Vx times delta r over 4r. And we are calculating for delta V, so that's delta V. And we're going to compare with the half bridge, this is a quarter bridge. Now looking at the half bridge, see what the delta V is over there. And you get a concept of why we are going to use a half bridge instead of quarter bridge. So half bridge Vex grounded R V1 V2 that's a change of the resistance because you mount two, one on the top, one at the bottom. So when you bend it, the first one is being stretched, but the second one is being squeezed. So it's a plus and minus. What is delta V here? Still V2 minus V1, which equals Vex R plus delta R over this plus this becomes 2R minus Vex, just 1/2, right? This becomes Vex 2R R plus delta R minus 1. No, minus 1 over minus this 1/2. And then this becomes 2R and wait, 2R. Then if I've got a 2R here, this is not changing, minus R, right? And this becomes 2R over delta R. Very interesting if you compare these two. Which one's bigger? Half bridge is getting a bigger delta V. So which one is better? The half bridge is better, it's more sensitive. The delta V, the same delta V is, the same resistance change is giving you a bigger delta V. It's already very small. Like I said, I was trying to measure the resistance change. It's like 0.01, 0.01 or 0.001 ohms change. Very small. And the third one is called full bridge. Even more sensitive. And now let's see how it's more sensitive here. This half bridge. Full bridge. R plus delta R, R minus delta R, R plus delta R, plus delta R. Delta V equals V2 minus V1. And here. And this equals V2 is Vx times R plus delta R over this plus this, which is 2R minus Vx times this one, is R minus delta R, which is 2R. Okay, so equals Vx 2R, R plus delta R minus R plus delta R, cancelled. This is Vx 2R 2 delta R, and this got cancelled. Okay, Vx delta R over R. If you compare this one with this one, it's twice as much as this one. So the full bridge is even more sensitive. Yeah, more sensors, yes. That's the cost of it, right? The load cell we have. So that's the load cell. It has 4 load cells in there. So the initial purpose of the kit is to let you guys build a bathroom scale. You can buy one for $20 on Amazon, but we are not doing that. And let's see where's the string gauge. It's definitely over here, right? It's being sealed by the epoxy. Okay, why 3 wires? Think the resistor only 2 wires, right? Why there are 3 wires? You can see why this is a low cell. Why it makes sense. Have you heard about cantilever? Cantilever. So see this part of the metal plate doesn't have any support. So this is a metal ring. So if you give a pressure here, right? See, you couldn't see it, but you can bend it. You can bend this part. This is the only connection to the metal. So if you open the back cover of the bathroom scale, you'll see that what you think and which one should touch the floor and which one should be mounted to the back of the plate. Which side should touch the floor? Here or here? I think no. I think this part touches the floor. They have something else on here, mounted here, like printed part on it. But this part, because you can see this is higher, it's taller, right? So it has a tip, like a tip to touch the floor, and this part is pretty flat, so it's just mounted to the back of the plate. Okay, and another question here, I just ask you guys, why there are 3 wires? No power. It's just resistor. Wait, look at the. So what's inside is this is actually a half bridge. I'm going to show you why it's not making sense. Just use a quarter bridge. Nobody use that. What's the reason? What's the reason for it? Not just because of sensitivity. It's because of temperature. So these string gauges are super sensitive to temperature change. I mean, these ones are just rod resistors and not changing the resistance over the temperature change. But this one changes a lot. Whenever the temperature changes, it has a delta R here. Is that the pressure or temperature? I couldn't tell, right? But if you have at least a half bridge, right? Whatever changes here will be canceled out. Not all of them, but they are able to, because they are calculating each side every time, right? So if here changes, then the ratio is not changing that much. That's why at least use a half bridge, never use a quarter bridge. So these ones, because this is a product, right? So these ones are two resistors inside, two strain gauges. So what's in here is you have to find out which wire is the middle wire, which wire are the two terminal wires. It shouldn't be that difficult to measure. You can just probe the terminal, then see which one's which. So it has the three wires like that. It's 1K ohm, 1K ohm. If you don't bend it, there are 1K ohm strain gauges. It has three wires. And now you can see you have two resistors for the bridge right now. If you want to build a Wheatstone bridge, you just need to grab two other resistors from the lab. One thing I don't know, I'm not sure is the resistors we have in the lab in the drawers, the rod ones, are really cheap. So they have probably plus minus 10% or something. I don't know. I think you might be able to figure it out by calibrating the reading later. You know, on the scale you have a tire, right? You just press it and tell the machine that this is 0 pounds, nothing on it. So you should be able to compensate it by doing that. And I think the libraries and code online and the example code I provide on my website is able to do the calibration for you guys as well. So let's try it and see what's going to happen. But in the future, definitely something being mounted to the horseshoes will be surface mount resistors, and I will purchase more accurate resistors instead of using the rod ones. But for building a prototype on a breadboard, I think it's okay. Might be okay. I'm not quite sure, but I think probably. And these wires are super thin, just one little wire. And you want to use the soft wire, the soft multi-stranded wire in the lab, solder to here. It's going to be a bit challenging to solder to this wire. It's too small. And the sensors are these ones. So you have to solder the header pins to here, right? Make sure it's vertical, perpendicular to the board. And these are 24-bit ADCs. So you know that it's super sensitive. So the Arduino ones are just 10-bit. It's 24-bit ADCs. Just keep that in mind when you are reading the values in your Arduino. You know what's happening. So it won't be 1023, 1024, right? Or reading the digital numbers. The maximum is 1024. It won't be like that. It'll be like more than 10 million or something. That many steps in there. You just need a one. Every one of you just need a one. So I got 4 here for all of you guys, and I got a lot of these sensors as well. Okay, and let's go to the website. See what are the materials I provided there, and what are the example code you have. Again, Thursday, no lecture. Just keep working on it. And this task is due next Tuesday. Okay, so the first video is not giving you too much information. It's just showing you that someone used that pressure sensor for the humanoid robots to balance the robot. And the performance of the robot is not even really good. I think this guy is still doing experimentation with the robot. It's just showing you why they need a pressure sensors for the feet of the robots. And this is another guy was trying to figure out how to solve the balancing issues, and eventually find out that the solution would be a pressure sensor, the strain gauge with a both cell being mounted to the lag. Okay, just let you guys know the applications. You know, this robot looks really awesome. It's something very similar to the one being invented in Boston Dynamics. Okay, and I was trying to see if there's an open source version available somewhere, and I searched on Amazon. $700 you can buy one. Smaller, it's just like this big. $700 can do the same thing. I mean, even more balanced by this one, probably because it's too small. can walk, can jump, can squat, can do a lot of things, and do visual recognition like the ones we have for the ESP32 cam. I'm trying to buy one and duplicate it here. And here's a tutorial you want to refer to, and probably some example code he submitted to the YouTube channel. He showed the examples of using 4 locales. Keep in mind, 4 locales doesn't mean he's doing a full bridge design. Remember, every single one has 2 resistors, right? It is a full bridge, but it's different from the ones we have on the paper. And he also showed the code and the results for just one locale. One locale has 2 resistors and have to use 2 other resistors to make the bridge. So this is one of the main examples you want to follow for this problem. So this picture shows you the concept or theory behind the strain gauges, right? Some examples of locales, different types of locales, and this is the one we are going to use. Okay, see the rigid mount. You want to mount the back of it to the plate, and the load is being loaded on the top. So for the bathroom scale, the load is actually at the bottom because the rigid mount is the plate. Like this one, right? It has 4 corners, has 4 locales like this. And this video shows you the resistance change. He did the same thing like what I did to damage that. I don't know if he damaged the strain gauge, but he was trying to bend it and see the resistance change. And you'll see how much it's going to change over there. So that's why I want to put it here so you guys don't have to try it in the lab. 0.011 ohms or something. And this is the data sheet for the module, right? The module has amplifiers and ADCs in there. So you don't need that. You don't need to build another amplifier for it. Here's a schematic diagram, and you can see if you build a Wheatstone bridge outside of the chip, and this is how you make the connection to the chip. Keep in mind, I don't think you have to. Let's take a look at it. I think these parts, the caps, we have been doing so many projects, right, using the cap. So what's the function of the cap? Very quick quiz question here. Why do they have a cap short as the ground? How it balances. So the right way to answer that question is it's a high pass filter, right? Remove the ripples from the DC power supply, or it's called ripples or high frequency noises to stabilize the DC voltage. So all the high frequency ripples or pulses will pass through that cap and be shorted to the ground. So remove the noise. I believe these parts are already soldered on the board, so don't have to do anything here. This block here is a chip, okay? But this is the module, it's a PCB module. It has all the peripherals over there. So I think it has resistors, the BJT, and the caps, a lot of things. So you don't have to do anything else. Just directly short, or just follow the video. Follow whatever this guy tells you to do. Try to repeat it. But he uses Arduino, and we do not use Arduino here because of the Horseshoe project. We use ESPs. So we have to use ESP32 to implement this project. And fortunately, this guy already did it for you guys. It's a very good example to follow. The only difference is he used a different locale. The circuit doesn't know. The circuit doesn't know what kind of locale you're using, right? You just need to make the correct connections. So I think the two major references here, right? One is this one, uses the ESP with the same module, but different load cell. And the second one is the Arduino with the same load cell and same module. And now let's see the two tasks. What are the two tasks you have? You use the ESP32HX711, which is ADC amplifier module, and two 1K resistors to build a pressure sensor. Because the load cell, the sensor here, has two string gauges in there. So you need two more resistors to build a wisdom bridge. And read the data into a serial monitor. So just need to have a snapshot. Shows that it is able to read the weight. Let me see how I want to demonstrate that. I would just record a video and use your finger to press on that load cell to see the changes. Okay. And the second task is to send the data over a second. Send the data to a second ESP module. And to the same display. So this is a very fundamental application. That's why I think it's reasonable for 1 week. Serial com, yeah, for the second one. And remember the examples for the ESP wireless communication, right? You have all of them in the microcontroller class. Just refer to that tutorial for that piece of code. Any questions on anything? No?
Wait, so sorry.
Wireless. Yeah. So wireless for the first one, no. The first one just the ESP as a microcontroller sends the weight and send it to the serial, right? The second one, you have one here sensing and sending wirelessly, and the other one receive it wirelessly and directly send it to serial. Yeah, because I don't want to add a LCD module to it. I prefer serial because it's faster. If you do LCD, is just a lot more things in there. So just do serial for display purposes, demonstration. Okay, let me give you the sensor.